Thanks. So today I'm going to speak about a theorem that I proved with Heo and Dale Winter. So you should assume that everything is joint work, except for possibly the last slide if I get that far. Okay. So let me give some motivation. I'm going to talk about some technical result, but I want to tell you why we ended up trying to prove this technical result. So there's two striking conjectures about continued fractions. So if x is in the interval 0, 1 of this form, so an infinite or finite continued fraction, so the AIs are integers, positive integers. We'll write x as this bracket notation. Do I have a pointer? No, maybe? Yes. And this expansion is finite if and only if x is rational. Okay, so the setup I want to have is that I'm going to have some finite alphabet A. And let C sub A be all the infinite continued fractions such that all the entries are in this finite alphabet, as in this expression, star. Okay. I have to push this so hard. Okay, and R sub A are going to be the approximants to C sub A. So they're going to be all the finite continued fractions with entries in this alphabet. Okay, and then just as background, something in C sub A for some finite alphabet A is called absolutely Diophantine. Okay, so let D sub A be the denominators of R sub A. So R sub A are some rational numbers, and I'll write them in reduced form, and then I'll look at their denominators. All the denominators that appear like this will be D sub A. And I just want to have this notation, the square brackets of A is 1 through A. And actually, yeah, I think for most of this talk, that's all I really care about. So Zaremba conjectured that there's some A such that every natural number appears as the denominator of an approximant in this finite alphabet. So, okay, I actually don't know the motivation for this, but, or not the motivation, but I don't know the intuition for why this should be true, but why he thought it should be true. And then this conjecture is established for a full density set of naturals by Bourgain and Gamburd. So they prove that there's a such that the growth of the denominators in the set 1 through n is n plus an error term, which is well, small o of n at least. Okay. And then there's this other conjecture of McMullen, which is going around as arithmetic chaos conjecture, which says there's some A, at least 2, such that for any real quadratic field K, if you take, if you look at the continued fractions of this form, so I wrote the bar for this sequence of symbols to repeat indefinitely. The size of the set, so L is the period. The size of this set grows exponentially in the period for each individual real quadratic field K. But actually, at the minute, we don't know that this set is non-empty for every single K. So, okay, these are very interesting. This is interesting. Okay, so. Right, so take you real quadratic field. So I have to provide. Okay, no, actually that's not the way it goes. I provide some A first, such that whenever you provide me any real quadratic field, the set of infinite periodic continued fractions on that alphabet of period L, the size of that set grows exponentially in L. That are in K. Yeah. So like, yeah. Actually, is it? Well, I mean, I'm saying it's open if it's non-empty for all K. Never mind, even empty. Is my understanding of it. Okay, so I'm not going to prove this in this talk, so it's just motivation. Okay, right. So McMillan had a heuristic. He has a heuristic for why this should be true concerning the existence of some horseshoe somewhere in some dynamical system, which is actually quite. It's kind of. I think. Yeah, this motivating example is actually very similar, if not the same, as the dynamical system I'm going to set up. Yeah. I mean, there's certainly chaotic dynamics going on here. Okay. So, motivated by these questions, we want to look at the lattice point count for this certain semigroup. Where the semigroup is parameterized by the alphabet. Okay. So let G sub A be all possible products of these elements. Okay. Then the connection with what I said before is that the denominators are given by this inner product. And then basically, just because you want to be in SL2, you pass this sub-semigroup, which is generated by products of two things, or just things that have an even number of terms. So this is going to be, gamma is going to be what I'm going to talk about basically for the remainder. So I claim gamma is a thin semigroup inside SL2Z. So it's not a group. I mean, this is going to be maybe relevant later, but there's no surface corresponding to gamma. Like if you had a subgroup of SL2Z, then you take a quotient of H by gamma, then there's some surface, but this doesn't exist here. So, okay, maybe it's not obvious how you start to deal with this. Okay, so what does thin mean? Okay, so consider this. Pick any origin in the hyperbolic plane or the Poincare disk, and I consider the orbit of gamma on this origin. Because gamma is acting discretely on the space, there's no accumulation points inside the disk, but there will be accumulation points on the boundary. So gamma O, this orbit, accumulates on the boundary of hyperbolic space. Okay, the action is by Mobius transformation. I'm going to write L of gamma for the set of accumulation points. This is called the limit set. And now I have this parameter delta, which is the Hausdorff dimension of the limit set of gamma. Okay, so the limit set of gamma should coincide with C sub A, these infinite continued fractions, when I work in the upper half plane model. So there's a direct connection. This limit set object is really the sort of very closely related to what you want to study to start with. Okay, so what is the Hausdorff dimension? So Hensley has this formula. So either from this formula or from the dynamics that I'll set up, you can see that if you have a finite alphabet, you have a Hausdorff dimension which is strictly less than 1. So I'm going to say that's thin here. And as we're about to see, gamma is free. Okay, so I have a thin, free semigroup inside SL2Z. So this is the main theorem I'm going to discuss for the rest of the talk. I want to put this norm on matrices, this Euclidean norm. We prove this theorem. Okay, so there's some modulus Q0 and some epsilon bigger than 0, such that when I'm co-prime to this modulus, Q is co-prime to this modulus, and it's square free, then for any psi in SL2 Z mod QZ, I have this congruence lattice point count. So I'm counting over elements gamma and gamma which have norm less than this parameter R, and I also want them to be congruent to psi mod Q. Then I have, so if I didn't have the congruence condition, this would be the correct main term. But because I'm in a congruence class, then I have to divide by this. And the power of this theorem is that there's the saving of epsilon in the exponent in the error term, and we allow this polynomial in Q. Okay, so quite a lot of stuff goes into this. So, you know, I think what goes into this is more interesting maybe than this theorem, or maybe the consequences of the theorem are more interesting than the theorem. Okay.
What did you say thin was again?
I want to say thin here is like you have so thin for a subgroup of SL2Z would be like its infinite index inside SL2Z. I don't really have a concept of index here, so I'm just going to say, I mean, in this case, where you have a SL2Z, a finitely generated infinite index subgroup, you have a delta which is less than 1. But I'm just trying to say that like it's sort of analogous here. But we have a Hausdorff dimension which is...
But is it related to the Hausdorff dimension in the limit set then?
Yeah, so like SL2Z or a finite index subgroup of SL2Z has full Hausdorff dimensional limit set. So in some sense we're like...
So thin means what, less than 1 or less than a half or what? Yeah.
Less than 1. Sure. Okay. So I've got 5 remarks to make about this theorem. When gamma is all of SL2Z, it's a classical result. From bounds on eigenvalues of automorphic forms, which bounds on eigenvalues which are uniform in the congruence aspect. So for example, Selberg's 3/16 theorem will give you like actual a quantitative error term, which is some multiple of 3/16 or 1/16 or something. Okay. The other remark is that instead of adding a 1 here, we can have like any nice enough function that extends to C1 on the boundary or something. So we can do sector estimates. Okay. So Bourgain, Gamburd, Sarnak proved this result with this error term. So not a power savings, but actually good enough for sieve purposes. When gamma is a thin, finitely generated subgroup of SL2Z, and in this difficult regime where delta is less than or equal to half, and they prove a uniform error term whenever delta is bigger than a half. Okay. So Heo and Dale Winter extended Bourgain Gamburd Sarnak result to get a uniform power savings error for any finitely generated thin subgroup of SL2Z. And this was a breakthrough to the level of difficulty required for the theorem I'm presenting here. Okay. And then, okay, so this connects with the motivation. The lattice point count of the theorem, it features in Bourgain and Kontorovic's work on Zaremba's conjecture in a way that suggests that an improvement on this type of error will lead to an improvement on the size of the exceptional set in Zaremba. Okay. Yeah, you would aim for a power savings error term. You would aim for yeah. Yes, this is the only issue. Okay. So, how do you approach this problem? Like, you don't have like a surface where you can start to study geodesic flow, or so you have to do something like you have to set up things yourself. Okay. So it turns out I'm going to work in the upper half plane model. It turns out that I can find intervals with a certain property, which is that if I let I sub A be these intervals, then GA maps basically let's just say everything into I sub A. So GA maps all the other intervals into I sub A. Okay. Okay. So this is basically what you want, but then okay, we pass to some sub semigroup gamma A. So we have to modify this in some way, but okay, it's just a technicality. So this is right. So for example, when A is 3, I have these 3 intervals at the bottom. Okay, and then like G3 maps these 2 into here, G2 maps the other 2 in here, and G1 maps these 2 in there. Okay. So as soon as you have this, as soon as you have this setup, you get that the semigroup is free by ping pong, because you couldn't have a relation between the generators, given that they're mapping the intervals inside each other in this way. Okay. So yeah, so I kind of want to get away from like the alphabet and A and all this. So I have some free semigroup generated by G1 through GK, and I have this orbit of this origin coming down to here, and I have these nesting intervals. So I consider the image of the intervals under elements in the semigroup. So I think I have some examples. So G1 of I1 is here and here. So we have some kind of like tree structure, and it goes down and down and down. And infinite intersections of nested intervals correspond to points in the limit set. And there's also some kind of like naturality between the way that the orbit comes, the orbit of this point has also got a tree structure, and this tree matches up with the nesting structure on the boundary. Okay, and we have ping pong. Okay, so yeah, one main theme is distortion. So if I just wanted to count elements in gamma with a certain word length in these free generators, I'd have quite an easy job, because I can just do this. I mean, I can solve the problem. I can solve the. I'd sum some geometric series. Like there's k generators, so I know how many things there are of each word length. I add this up. I have this uniform error term. Okay, but this is not really the right thing. I don't want to count with respect to word length. I want to count with respect to this Archimedean metric. And by the way, if you did want to count like this with respect to this combinatorial word length metric, you can use expansion for heliographs as a black box to get, like for the congruence version of this, to get a power savings error term. Okay. So that's not going to be the case in what follows, because things are going to be distorted, so we have to go into expansion a little bit. Okay, so our topic is harder. We want to count the number of orbits inside a ball of radius t in the hyperbolic metric. This is equivalent to the theorem I said before. Okay. You translate using this identity between the norm I defined before and the distance in hyperbolic space. So if you want a really coarse estimate, it's true that mapping gamma to gamma O is a quasi-isometry. So you get something very coarse like this for some positive constant C. You can count like this, but this is terrible basically. Okay, so yeah, so you don't have any main term. The correct main term is given by the Hausdorff dimension. And actually there's more than this, there's more information about the distortion. There's a function that lives on the limit set mapping into R called the distortion function. And it measures what you want, the distortion between the word and the Archimedean metrics. And it turns out that you can extend this distortion function to real analytic function on I, and this is actually important. Okay, so where does this distortion function come from? So I have like words in the semigroup. I can define a shift where if I have this word, I'll just cut off the first entry. Okay, so I'm shifting. I have to add in one here though, because what if I just have one element that I'm mapping to the identity which wasn't in my semigroup to start with? And then I'll define this function here. So this is not going to be the distortion function, but it's going to be, so the distortion function lives on the boundary. This is like an analog of distortion that lives inside, and then distortion on the boundary will be like a limit of this. So the distortion is the difference between these two distances, between gamma and its shift. Okay. So then if I actually take the limit, like of some orbit going onto the boundary, then this is the distortion function I was telling you about. The limit of this one. Okay. So basically what's going to happen is we're counting lattice points inside hyperbolic space. We want to move this counting onto the boundary. We have some dynamics on the boundary and we're doing everything there. I mean, the heuristic is that you're counting inside hyperbolic space, but really everything interesting eventually happens sufficiently close to the boundary that you can replace and go onto the boundary. So what happens to the shift? The shift's like cutting off the first entry of an element. There's an analog of this at infinity. So I define this map T taking I, which was the union of all my intervals, and it's going to map I to, I'm working in upper half plane, the whole of the boundary, so it doesn't preserve I. The way I define it is T restricted to I sub I is G sub I, the inverse. Okay. And then if I have this definition, so recall, okay, if I have this definition, I define distortion to be log of the derivative of T. So, okay, what am I actually doing here? G sub I are Mobius transformations. So that this derivative is just like the derivative of a Mobius transformation, and this function is real analytic because it's, you can check. take the derivative of a Mobius transformation, like, okay. And if I want to get the limit set back from this dynamical system like T and I can take this intersection to get the limit set back. So you could just start from here. Okay, so I want to do this lattice point count. What I have going for me is that I have this tree structure. I have this free semigroup, so I have some structure there. What I have going against me is the warp metric, the warped distortion function. But because you have this, you can do recursion. Like I'm counting over a tree. I'm not counting like the obvious thing, but I can still write a recursion down. So this n star is like some quantity. It's basically exactly what I want to count. It has an extra parameter gamma naught which allows for the recursion. If I want to write a recursive function, a recursive version of some other function, I add a parameter that I can thread through. Okay. So n star is more or less what you want to count when gamma naught's the identity. And because you have this recursion, you get this renewal equation. So this renewal equation is actually a very elementary thing. It's like you could think of it like integration by parts or something on a tree. Okay, so I have all this stuff on the left-hand side that lives inside hyperbolic space, and I have all this stuff on the right-hand side that lives on the boundary, and I do all these replacements. And I just argue that I basically to deal with this new counting quantity. So A is like the parameter for the lattice point count. It's the counting parameter. And I have this notation. So this is actually going to be very important. So tau to the upper n of y is, I take y, I go along the orbit under T, and I add up all the taus I get along this orbit. So it's a distortion along a trajectory of T. So this quantity here, I'm just counting how many trajectories I have with a certain amount of distortion. And actually, yeah, there's some bridging. So let me go back and say something. This passage is due to Lally. So it was known for like quite a while. You have to do a little bit extra work because Lally only wanted to get a main term. If you want to move an error term from the boundary inside, then you have to do something slightly more than what he did. Okay, so the behavior of distortion is critical, and also the behavior of this sort of iterated distortion is also critical. So you want to take a Laplace transform in the counting parameter. So this is like the prime number theorem. Like it's much more natural to prove prime number theorem on Fourier's side. Like, so you're changing A, the physical parameter, to frequency. So we're going to have a new parameter S. S is frequency parameter associated to our counting parameter. And if you take the Laplace transform of this whole, this equation here, I don't know if you can see this in real time, but if you squint at this, somehow I think you're going to move to infinity and take a Laplace transform, okay, then you get something like, that looks like this equation, and just take my word for it. Okay. So what's this L sub S? It's what came out of like the recursion after taking a Laplace transform. So this is going to be a central object. L sub S is a transfer operator. It acts on this Banach space C1 of I. And it sums up over past histories of T with some factor which, this e to the minus S tau, it involves distortion. Okay. And then this e to the minus S is coming from like this kind of business here. Okay, so what do you have to do? So that setup is just what you need to do if you want to do the lattice point count with no congruence condition. If you want to do congruence lattice point count, you do the whole thing again, but you twist off by some unitary, you send the vector valued functions and you twist off by some unitary on the vector space. So the unitary is defined in a natural way. So that was the vanilla transfer operator. The new one has this twisting factor in, this C sub q. So what is C sub Q? How do I look it up? So Y is in I. How do I look up what this should be? What should I twist by? I just look up what the GI is, and it's in SL2Z, I reduce it mod Q. So, yeah, so at this point I think this is where I'm missing my slide, which wouldn't photocopy, so yeah, let me just write something on the board. Okay, so I need a light as well, maybe. Yeah. So here's what you want. Okay. So you need two things to happen to get what you want for the lattice point count. You want, in any case, strong spectral bounds. So you have an operator on Banach space. Okay. And there's two aspects that are going to be present. The first aspect is large imaginary part of S. Okay. So there's two aspects. So the first one is the imaginary part of S is large. Okay. So something very useful happens, which is that you can sort of treat these two aspects separately. So one reason why this is true is because this thing I twist off by this unitary, it's locally constant. So if I ever want to take derivatives or anything, this has no derivative. So when I run through the real dynamics, this CQ doesn't interfere with what I'm trying to do. Okay, so what is the critical behavior? So forget about Q. I'm going to write this symbol to mean I only write the terms that actually matter. So it's like the way this acts is like this. So I sum over y such that t of y is x. And then the critical term is something like, if I write S is A plus IB, I'll get something like e to the I, let's see, minus I B times tau of y times f of y. So that's the critical piece. This is the thing you have to control. Okay, and then where did I like switch this around? And then I'm going to.
You seem to be just working any S now.
Yeah, S has to be close to delta.
On the line of conversion.
So the real part of S is, yeah, close to delta. To the left, like inside where you. I mean, I'm going to say more about each of these two scenarios. It's like my remaining two sections is like I explain how you deal with these behaviors. Okay, and then the other aspect is you can find gamma 1 and gamma 2 where there's non-equality here by using this trace identity. This trace identity. So if these were equal, forget about absolute values. If these were equal, then their commutator would have to be unipotent, and you just find a way to get out of this.
You said what's a bit perplexing here is Dolgopyat gives exponential saving, and
Yeah.
stationary phase argument will give you a power in T where S is sigma plus IP. You completely suppress the real part, which is presumably the exponential gain is coming. Was that not true? I mean, so you're complexifying. The real analyticity you're using somewhere else in order to make sure that you have this derivative strictly.
Yeah.
So
There is a cancellation because you're going in the
I in the
negative.
T, yeah, but the I in the T would give you T to a power, and you need exponential gain in. I'm a bit confused about this.
I have a question because I think Dolgopyat is something for for a high imaginary value, you have analytic continuation in a ball with
Yeah, so that's exactly my question. Yeah, is it the ball to the left? Are you moving then uniformly to the left of real part of S equal to delta.
Yes.
Yeah, basically.
Okay, okay. So it's uniformly to the left, giving a zero for hole-free region.
You end up with like it's this contraction is uniform. And then
Right, but that's coming from the location of the real part. But the ball, if the ball is uniform when you go high up, then you're done. I agree. Or maybe that positive derivative makes it uniform.
I think that's what Dolgopyat did, if I remember.
Okay, so you are on the line delta, but you're getting a uniform
you're close.
ball no matter how high up you go.
Yeah. So this is kind of amazing. Okay, so we need to do this for vector valued functions, and there's a C sub q around. So Heo and Dale Winter worked out how to do this. They did it first. Okay, so that's the real dynamics. I just want to give like an idea of what's going on. Basically, you're bootstrapping something simple to something amazing. Okay, so what happens mod P? I mean, this is going to be very quick, but there's this expansion machine of Bourgain and Gamburd. So I have some fixed set of generators inside SL2Z. And if I want to prove that the Cayley graphs of the projection of these generators to SL2FP are expanders, I consider measures like this. So I put an atom on each of the projected generators and divide by the size. So I have some probability measure. And then my whole strategy will be like to prove that this probability measure is a contraction as it acts by convolution. This is not really, I mean, okay, so for completeness, the first stage is to use large girth and then work with Keston to get some initial saving, to get to some initial point with some, you iterate your measure, the convolution of your measure, to some initial size. And you use girth to get the, this is not concentrated on proper subgroups, or you have something to start with. And then you're going to also iterate this a bounded number more times to get savings, unless there's some set inside SL2FP which doesn't grow under tripling. This is just for completeness, I go through this. And then there's some miracle at the end where you're pushed over by the representation theory of SL2 of FP or FQ. Okay, so how does this apply? So when you iterate this thing, this LSQ, some measures crop up, and you end up, if you want to prove that this thing is like contracting, it's enough to prove that these certain measures that crop up are also contracting. So these measures have similar properties to the measures that you get at this initial stage. So you're iterating this congruence transfer operator, and you get these measures appearing, and then you start into this at this point. Like, But okay, so this initial saving that you're getting, like this initial point, in the case of a Cayley graph, you're getting it from a girth assumption. But in the case of these transfer operators, the saving comes from the expanding property of the map, hyperbolicity. And actually, the details of this were worked out for squarefree moduli by paper of Bourgain and Gamburd Sarnak. Okay. And yeah, method of. Okay. But if I wanted to do the same thing, like in the real dynamics, I identified what is the source. The source comes from real analyticity and some absence of unipotence somewhere. It's pretty simple.
Basically, what we did in our paper, there's the Archimedean aspect, and then you have the Dolgopyat, etc.
Yeah.
Then once you got into the modular part, it was basically an independent parallel stock.
Yeah.
So what you're really doing is putting these things.
Yes.
There was a problem there that somehow when you have small q,
Yeah.
you were losing some uniformity, so you couldn't quite keep
Yeah.
the strip all.
Yeah.
So basically, to overcome that somehow, you have to exploit these Dolgopyat operators also
Yes.
on the level of the mod Q.
Yes, I'm trying to draw the
Yeah.
parallel. Yeah, I think you could
So
draw.
we were kind of afraid of mixing these things. So that's what is going into paper.
No, they're separate. Like the mod Q stuff was done in your paper. I mean, we didn't do anything new really, apart from some details about random
Now,
walk.
how do you keep the strip uniform? Because you're having a uniform strip which does not.
It's the Dolgopyat, Dolgopyat
So
scheme.
we had the problem of this small
Yeah.
cube. So at that point you have to gain rely on something.
Yes. But they somewhat stay independent because the CQ, these co-cycles are locally constant. It's like having a flat vector bundle. If you want to prove a spectral gap for a flat
So
bundle.
for small q you're reducing again is Dolgopyat operator?
For small.
So you're
much,
using this
it's in the Archimedean case without Dolgopyat you can't get any zero-free strip.
Now what I'm saying is that for Q in the modular part, we did not rely on Dolgopyat at all.
Yeah.
Right.
No, we didn't state our theorem for going into the modular, going into the Q naught. Is that what you mean?
So what is how do you manage to keep the strip to avoid that the strip is going to narrow when the
That's
magic part
It's Dolgopyat. Yeah.
What?
Dolgopyat.
Yeah. So you're going to use Dolgopyat also in part B.
No.
At least for maybe not for large Q, but for certain values of Q.
Maybe large Q wasn't the right thing to say.
For large Q you don't need it.
Yeah, maybe large. Yeah.
Let's say if you go in your imaginary part up to height T, something.
Yeah.
The problem are the Q's which are, I forgot what it is, something like logarithmic, smaller logarithmic infinity or
Yes.
something. Because you don't get enough spectral gap
Yes.
from the Q.
Yes.
So how do you get around that?
You're using the ideas of Dolgopyat.
So you're using Dolgopyat
Yes.
in the modular case.
Yes. Yes.
That's what
Absolutely.
I'm asking you.
Yes. Oh, yes. So they. Yes. I'm sorry. So all this account that I was giving before, like all this stuff, there's a modular aspect around, but you want to do stationary phase analysis for a vector valued function. You're valued in.
When T gets large, you can be quite crude, even when you're high up, which is the basic problem. Of course, he has to keep track of dependency Q everywhere.
Yeah, well, this is only for the small Q.
Right, agree.
But yes, this is not new in our work. Okay. And then really where this mod Q stuff is coming from is in the Helfgott results on tripling, which is in the heart of this stuff. There are trace identities, and then something that's more sophisticated, I think, than what happens in the real dynamics is the sum product theorem. So this is what it boils down to. This is the source of your savings in the modular aspect. And then the work I have in progress is to extend to prime power moduli. Okay. So the ideas are again fundamentally different. So I have these two aspects that I talked about, real dynamics and square-free dynamics. And so we want to generalize to powers of prime.
Where the square free case will done, right?
Yes.
Okay. So now the problem is to get general.
Yeah. And this is totally different again. It's fundamentally different from either of the previous cases. Some products is still going to be in there, but then you're boosting, you have to prove some growth result. Your boosting is to do with Solovay-Kitiev. Okay. That's what I've got to say. Thanks for listening.